For the last lecture of this week, we will look at a topic that's becoming extremely popular in recent months, which is self-attention and transformers. One question that we left behind in an earlier class on visual dialogue was, what are other ways in which one can evaluate visual dialogue systems? Hope you had a chance to think about it or look for it online. One answer to this question is to look to natural language processing for getting performance metrics from the text domain, which could measure consensus between answers generated by a model and a relevant set of answers. If you'd like to know more about such an approach, please see this recent work called A Revised Generative Evaluation of Visual Dialogue. This work also talks about how one can generate a set of relevant answers. So let's now come to transformers. An acknowledgement: most of this lecture's slides are based on J. Alamar's excellent article on the illustrated transformer. So you can assume that any images that are not credited are adapted or borrowed from J. Alamar's article. Let's first try to understand, why does one want to go beyond RNNs or LSTMs for sequence modeling? So sequential computation prevents parallelization. So if you had a series of layers, let's assume you have a linear layer followed by an LSTM layer, followed by a linear layer, followed by an LSTM layer. When we say LSTM layer, we mean a series of LSTM blocks that process a sequence of inputs. So if you had an architecture that's similar to this, you could consider some of the architectures that we had for complex tasks such as VQA or visual dialogue could have had such a sequence of layers. When you have an architecture such as this, it's not possible to parallelize the processing of information through such a pipeline. Can we overcome this is a question we want to try to answer. Further, despite the availability of GRUs and LSTMs, RNNs can only maintain information for a limited period of time. If you have a very long time series data, for example, a chapter of a book, will an RNN hold the information, or a GRU or an LSTM hold information for a very long time series? Possibly not. Even in that scenario, one perhaps needs attention to focus on the right part of the previous content. We saw this with models for, say, visual question answering or visual dialogue, all of which used attention, not all of which, at least some of which used attention to be able to focus on the relevant parts of the previous sequence information. So if we are anyway using attention in RNNs, why use RNNs at all? Attention can anyway tell us which part of a sequence to look at while giving a specific output. So if you are doing, say, machine translation, while you are generating a particular word, you can decide which part of the input sequence should I focus on. You maybe don't need an entire RNN to hold the hidden state across multiple time steps. That's the hypothesis for transformers, which we'll talk about in this lecture. Transformers were first introduced in this work called Attention is All You Need, published in NeurIPS of 2017, which introduced an encoder-decoder framework to perform sequence-to-sequence modeling without any RNNs. This work proposed the transformer model, which introduced the self-attention mechanism without any recurrent architectures. There were few key components of this architecture, a concept known as self-attention, then multi-head attention, positional encoding, and an overall encoder-decoder architecture. We'll see each one of these in detail. What you see on the left here is the overall architecture. Hopefully, this would become clear over the next few slides. So a quick summary of how transformers work. If you considered a machine translation task, let's say you want to translate this input into the output which states I am a student, we are proposing the use of an encoder-decoder architecture, where in the encoder you have several encoder modules, each of which feed into the encoder at the next level, and all of these, and the encoder at the highest level feeds into each of the decoder which has a similar stacked architecture, and the final output is I am a student. Each encoder has several components inside it. There is a self-attention module which outputs a vector for every input word. So if you had a sequence of inputs, for each element of that sequence you get a certain representation as an output of the self-attention module. This representation is passed through a feed-forward neural network to give you another vector as output, which is passed on to the next encoder layer, and so on. Let's see each of these components in detail. Let's start with self-attention, which is one of the unique features that this work introduced. So let's consider two input sentences that we'd like to translate. One sentence reads, "The animal didn't cross the street because it was too tired." And the second sentence is, "The animal didn't cross the street because it was too wide." For a human, it's evident that the first "it" corresponded to the animal and the second "it" corresponded to the street. But for an RNN-based model, this is difficult to catch, and that's the reason self-attention brings value. Self-attention allows the model to look at what are the other words that need to be paid attention to while you process one particular word. The reason it's called self-attention is, given a sequence, when you're processing one element of that sequence, you make a copy of that sequence and see which other parts of the same sequence are important to process this element. And that's why it's called self-attention. So now if you had to draw a parallel to RNNs, you would see that you perhaps don't need a hidden state to maintain the history of previous sequence inputs. Whenever you process one element of a sequence, at that time you process an attention vector over an entire sequence. You don't need to store a compressed hidden state that has all the sequence information in one vector or one matrix. That again is the idea of transformers. So let's see how the self-attention is actually implemented. So the first step is, given an input vector, which is an embedding. So let's say you have a phrase thinking machines. So you consider the first element of that sequence, thinking. You would get a word embedding. Once again, assume that this is done using some text processing techniques to go from thinking to an embedding. An embedding is a vector representation of the word thinking. Similarly, x2 here is the vector representation of the word machines. So given these inputs to the self-attention module, there are three vectors that the self-attention module creates. These vectors are known as the query vector q, a key vector k, and a value vector v. We'll see how these are used very soon. But how are these vectors created? To create the q, k, and v vector, one uses learnable weight matrices wq, wk, and wv, which are multiplied by the input x to give us q, k, and v. So in this particular work, q, k, and v were 64-dimensional vectors, and x by itself, which is the embedding of each word in the sequence, was a 512-dimensional vector. One question here, does q, k, v always have to be smaller than x? In this case, you see that x is 512-dimensional, q, k, and v are 64-dimensional. Does this always have to be the case for transformers to work? The answer is no. This was perhaps done in this work to make computation of multi-headed attention constant. We'll see this very soon. What are the dimensions of WQ, WK, WV? You should be able to get that from X and QKV. You would have 512 cross 64. Those are the weights that are learned while you train the transformer end to end. So once you get your Q, K, and V vectors for each word in your input sequence, step 2 in self-attention is to compute what are known as self-attention scores, which is the score of all words of the input sentence against this particular word under consideration. So if you had the word thinking, which is what you were processing, you would compare this with every other word in the sequence and compute a self-attention score. How is that computed? Let's see. It's by taking the dot product of the query vector with the key vector of the respective words. So for this input thinking, the first score would be q1 dot k1. That's the query vector, which is q corresponding to the word thinking, and the key vector corresponding to the word thinking, q1 dot k1. Similarly, you would compute q1 dot k2 for the second word in the sequence, q1 dot k3 for the third word in the sequence, and so on and so forth. These scores are then divided by the root of length of k, which is the dimension of the query, key, and value vector. In our case, the dimension was 64, so the root of the length would be 8. So the score q1.k1, which was 112, would be divided by 8 and you get 14. Similarly, q1.k2 was 96 and that would get divided by 8 and you get a 12. This is known as scaled dot product attention. You can recall our discussion in the first lecture of this week where we spoke about several kinds of attention alignments, and scaled dot product attention where you take a dot product and then scale the value is one such alignment mechanism. Why do we do this here? Scaled dot product attention helps get more stable gradients by scaling the values to a manageable range instead of letting it go too high or too low and the variance be too much. Once this is done, the next step is to use softmax to get a distribution of the attention of each of the words in the sequence with respect to the word under consideration. So once you get these scores 14 and 12, you can do a softmax on them to get a weight for the first word, a weight for the second word with respect to the first word. We are still processing the first word here. Obviously here, this score of the first word with respect to the first word is likely to have the highest weight, because you would expect that to process the first word is the most important word. However, we still have weight or attention vectors, attention values over other words in the sequence, which also add value to processing the current word. As the next step, we multiply the softmax output with the value vector that we got earlier. Remember, we had a query, key and a value vector. We now use that value vector with the softmax output to now get a weighted representation of the value vector. Similarly, you would have a weighted representation of the second value vector, and so on and so forth for every sequence, for every input in the sequence. And we finally then do a weighted sum of all of these V1, V2, V3 and so on vectors to get a final Z1, Z2, so on and so forth. So Z1 here is the weighted sum of V1 into softmax plus V2 into its softmax value plus V3 into its softmax value will together form Z1. Similarly, Z2 would be formed when we process the word machines. What do we do with these Z1s? Before we go there, let's try to summarize our discussion so far. So you have your input embedding X. You see two rows in X here corresponding to vector representations for two words, thinking and machines in this particular case. Then you have the matrices WQ, WK and WV. Those are learnable weights. And when you multiply X and that weight matrix, you get a Q, K and V. Then you do a dot product between Q and K, scale it by the root of the dimension of the K vector, do a softmax on it, multiply with the V vector, and that gives you your Z vector for each of your words in the input sequence. Now let's move on to multi-head attention. So we've seen self-attention so far. The next we'll talk about the component known as multi-head attention. Multi-head attention are these different layers that you see in the illustration here. Instead of using only one WQ or one WV or one WK, Transformers suggests to have multiple such WQs, WKs and WVs. So you would get multiple such query vectors, key vectors and value vectors. So, and you would do multiple such self-attention computations, and you finally then concatenate and send them through a linear layer. How does this help? This expands the model's ability to focus on different positions. So different WQs, WVs and WKs, weight matrices, could help the model focus on different parts of the sentence which could together enrich the processing of the current word. Secondly, it also gives our self-attention layer a sense of multiple representation spaces instead of choosing only one set of weight vectors. And getting these different representation spaces and then concatenating them and sending through a linear layer gives us better performance at the end. This part of transformers is known as multi-head attention. Here is the illustration. So if you have your input sentence, in our case it's thinking machines, we embed each word, each row of X is an embedding of thinking and machines. We have multiple WQs, WKs and WVs. In this case we see 8 such heads resulting in 8 query vectors, key vectors and value vectors. We get 8 different Zs, and then we use a linear layer to combine all of those Zs to get one Z for each input of the sequence. So you see here that there is something called R. R simply indicates that in your transformer architecture there are multiple encoder layers. The first encoder layer receives X as the input. Every other encoder layer receives the output of the previous encoder layer as input. That is denoted by R. So the original sentence and the words may not be given as input to the second encoder in that set of stacked encoders, but it would be the output of the first encoder that's fed there. A third component of the transformer's architecture is known as positional encoding. Unlike CNNs and RNN encoders, attention encoder outputs do not depend on the order of inputs. Why? Because you can choose to focus on what you want irrespective of the order of the inputs. Having said that, it still is important as to which position a particular word is in a sentence to make meaning out of it. So how do we bring that value into an attention model, into a self-attention model? That is done in transformers using an approach known as positional encoding. So the position of a word in a sequence is given as a separate input along with the X embedding. How is this position encoded? You could do it in different ways, but the paper suggests one specific way, although this need not be the only way. It takes the position of that particular word with respect to the sequence and processes it as a sine and cosine signal, and that becomes a positional encoding of that word in the sequence. This is given as input along with what we saw as X in the previous slide. So given thinking machines, if you took the word thinking, you would get a certain word embedding. You concatenate the position encoding along with that, that becomes your input to your self-attention layer. So the role of position encoding is to bring some value of where in the sequence a specific input which you are currently processing is. Finally, to come to the architecture of the entire model, as we mentioned so far, it is an encoder-decoder architecture. Let's first see the encoder. The encoder is a stack of 6 identical layers in this particular transformer that was proposed. Each of such 6 layers looks somewhat like this, what you see in the image here. So you have a multi-head self-attention layer, which we've already seen. Self-attention, take multiple heads, concatenate, and then have a linear layer to get a vector input. And that's fed in to a fully connected network, feed-forward network that you see on top. But between the multi-head attention and the feed-forward layer, there is a residual connection and there is also a normalization that happens before that output is fed to the feed-forward layer. So you first perform multi-head attention, then the input also comes through a skip connection directly to the output of multi-head attention. There you add and normalize the Z output that you get out of multi-head attention and the X plus P input, that's X plus positional encoding input that you get before the multi-head attention. You would add them, normalize them, that is fed into a feed-forward network, once again adding and normalizing, and that is the output of one encoder module. You would have six such encoder modules in this transformer architecture. And all the sublayers that you see within this particular encoder layer output data of the same dimension 512 in this work. Similarly, the decoder also had 6 identical layers. Each layer again has multi-head attention and a feed-forward network. Again, you have a residual connection and a normalization step that's done before the output of multi-head attention is given to feed-forward layer. There is only one difference here. This initial step also performs what is known as masked multi-head attention. The goal here is to not let the architecture see further words in the output sequence when it's processing one specific word. So if you're translating from English to Hindi, you wouldn't want, if you're now trying to process the third word in the output, at that time you can use attention on the first 2 words, but you don't want to use attention on the remaining words because the model is not supposed to know them while predicting the third word. This is done by masking the attention mechanism in the first decoder, and then on the outputs are passed on as it is to further multi-head attention mechanisms. That's the architecture of the decoder. So here is a revisit of the complete architecture again. The input embedding, then the positional encoding concatenated, you have the multi-head attention mechanism, then you have a skip connection, add and normalize, feed forward, add and normalize. You have ideally 6 such stacked encoders, and similarly you have the decoder as we just spoke, which has a masked multi-head attention mechanism, add and normalize, then a multi-head attention mechanism, add and normalize, feed forward, add and normalize, and you once again have 6 such modules stacked on top of one another. So the scaled dot product attention can also be visualized this way, where you have Q, K and V. You first perform a matrix multiplication of Q and K, that gives you your dot product. Then you scale the dot product, then you may choose to mask it optionally depending on which module you're talking about. Masking is done only in this first part of the decoder here. Then you apply the softmax, then multiply it with V, and that becomes the output of the scaled dot product attention module. The homework: there is a transformers in action video provided along with your lecture slides for this week. Please watch it to understand how transformers work. Also, the excellent article by JLMR on the illustrated transformer. And if you need to understand positional encoding better, this specific article by positional encoding on positional encoding. And finally, if you need more information, the original paper attention is all you need. Let's end this with one question. Are transformers faster or slower than LSTMs? What do you think? And why do you think so? Think about it, and we'll discuss this the next time.